and gentlemen, and welcome to section 6.6, and we're going to talk about specifics in a moment, but I'd like to pose two questions to kick us off into the lesson. First of all, are the two triangles similar here? Explain. Well, which triangles are we talking about? We obviously see one triangle here, but then our second triangle is this large one that contains the smaller one. So to know they're similar, we have three methods. We have angle-angle, we have side-side-side, proportions, and side-angle-side, proportions, not the congruence one. So in this case, we don't have any measurements for sides, so we can't use side-angle-side or side-side-side, but let's see if angle-angle can work. We see that they share an angle here, and we also see that these lines are parallel, or segments are parallel. So that means that these corresponding angles are congruent. So yes, we have AA, so they're similar. Take note of that, example number one. Example number two, if triangle SAM is similar to triangle DAN, is segment SM parallel to segment DN? Explain. Well, if these two triangles are similar, then we know that all of our angles are congruent, all of our corresponding angles, shared angle here. So are these two line segments parallel? The answer is yes, because corresponding angles are congruent. So yes, because the converse to the corresponding angle postulate, which states if we have corresponding angles that are congruent, then our lines are parallel. So example number two, take note of that. We just did, as informally proved, the two theorems we're going to talk about in the first half of our lesson. The title of the lesson is using proportionality theorems, and here are our first two. Let's say we have a triangle within a triangle formed by parallel lines. Those triangles are similar, which means we have proportional sides. So QT is proportional compared to TR when we compare SU and RU. So we have several proportions here, one of which can be seen down here. We know that RT over TQ is equal to RU over US. So that's a proportion we can write. We can also say that QT over SU is proportional or equal to TR over UR. So we can write a proportion. The converse is true as well. If we have proportions, because these are similar, then these lines are going to be parallel. So if we have proportional sides, that means we have similar triangles, which will mean we have corresponding angles congruent, which will mean these lines are parallel. So that's the converse of our proportionality theorem. If we have proportions, then we have parallel lines. The original said if we have parallel lines, then we have proportions. Let's do some problems. Whoa. All right, in the diagram, we're given these lines are parallel, and we're given some angle measures. What is the length of RQ? Well, we can write a few different proportions here. One is we could write, well, let's call this x for now, just to make it easier when we're writing. We can say x over 9 equals 4 over 6. We can also take the reciprocals and say 9 over x equals 6 over 4. We could say 9 to 6 equals x to 4. Comparing our two larger and our two smaller. Or we can also say, as a special one, we could say that x, which is the small piece, over the whole thing, which is x plus 9, equals 4 over 10, the whole thing. So we could write tons of different proportions here. I'm just going to solve the first one, because if we solve any of these four, we'll end up with the same answer. So 9 times 4 is 36, equals 6x. And divide both sides, x is 6, but we're not asked to find x, we're asked to find RQ, so we should write RQ equals 6. Let's try another one. On the shoe rack shown, we're given some measurements. We're told that AB is 33. We're told that BC is 27, CD is 44, and DE is 25. Explain why the gray shelf is not parallel to the floor. Well, the converse of our theorem says that if we have proportionate sides, then we have parallel lines. Well, here, let's check and see if we have proportionate sides. 27 over 33 should equal 44 over 25. But they're not equal. Improper fraction, proper fraction. Greater than 1, less than 1. So we won't. Because the converse says if we have proportionate sides, then we end up having parallel lines. Contrapositive says if we don't have proportional sides, we don't have parallel lines. So that is our explanation that I just gave to you verbally. Now you might ask yourself, well obviously we can look at it and see that it's not parallel to the floor. But that's not the explanation I want. The explanation I want is the mathematical explanation, some sort of evidence to prove it. Because we always need mathematical evidence for things that we're doing in geometry. Two more theorems. One is 6.6, no special name here. It says that if three parallel lines intersect to two transversals, then they divide the transversals proportionally. So in other words, we have proportions using these little segments in here. So you can say that UW to WY equals VX to XZ. Or UW over VX equals WY over XZ. All kinds of proportions you can write here just like before. And our last one states is if we have an angle bisector, we have some proportions as well. So let's say that ray CD is an angle bisector. We see these congruent halves here. That means that if I were to compare my two sides to my two sections formed, I have another proportion. So AD over DB equals CA over CB. So I have proportions here as well. Let's do some practice with that. In the diagram, angles 1, 2, and 3 are all congruent. We're told some measurements here. Find the distance HF between Main Street and South Main Street. We are measuring in yards here. Well, I have three parallel lines. How do we know? Because we have corresponding angles are congruent. So that means that these lines are parallel. If these lines are parallel, I have proportions. I have my small pieces up here compared to my large pieces down below. So I can write a proportion based upon the first theorem from today. So I can say that 120 over, let's call this x, equals 150 over 300. And if you cross multiply, you end up with x is 240. But that is not our answer. We're asked to find HF. We found HG. So HG, we need to write that plus GF to get HF. So if we add these two together, we end up with HF equaling 360, and that's in yards. Let's keep moving and do one more. This is a beautiful problem. So in the diagram, angle QPR is congruent to RPS, and we're told that here. Use the given side lengths to find the length of RS, segment RS. Well, since these are congruent, we know this is an angle bisector, which means we have some proportions. So 7 over 13 equals this guy over this guy. So this bottom part is x. We don't have anything labeled for the top part. But if this whole thing is 15, then this top part is 15 minus x. So the whole thing, take away this guy, we're left with up here. So it's 15 minus x. We can cross multiply now. So we have 195 minus 13x when we distribute equals 7x. If I add 13x to both sides, 195 equals 20x. And if I divide both sides by 20, x should equal 9.75. So there's just a few brief examples for this particular section. If you have any questions, feel free to email me, and we'll be talking more soon.